Picture an autonomous vehicle cruising down a sunlit highway. The weather is beautiful, sensors are spotless, and the software is running without a single bug. Then, out of nowhere, the car slams on the brakes, the tires smoke, the cabin jolts, and yet the road ahead is completely empty. How does a machine with perfectly functioning hardware and flawless code still make a catastrophic error? Early prototypes, like the one you see here, were built on a simple assumption. Feeding a computer accurate physical data would result in perfect driving. Engineers quickly discovered that flawless hardware has limits. The real danger lies in the physical constraints of the sensors themselves and the unpredictable nature of the open road. In automotive engineering, managing this specific uncertainty is known as safety of the intended functionality, or SOTIF. To achieve true autonomy, engineers have to stop trying to build unbreakable parts. Instead, they must program the machine to recognize its own sensory illusions, teaching it to doubt exactly what it sees. Let's look at a standard highway scenario. A self-driving car is approaching a common metal overpass or a large overhead sign. The car uses radar to scan the path ahead. Radar is an excellent tool for measuring the exact distance and speed of objects in any weather, but it lacks the vertical resolution to accurately judge height. This diagram shows what happens when radar waves bounce off that overhead sign. Because the radar cannot determine the altitude of the object, the system's logic incorrectly maps those radio reflections as a massive stationary truck parked directly on the asphalt. The car thinks it's about to hit a brick wall, triggering a phenomenon known as ghost braking. The engineering solution to this is cross-validation. Instead of relying on radar alone, the car asks its optical cameras to double-check the space. The camera visually verifies that the road underneath the sign is actually empty. When the sensors disagree, the car falls back on a strict majority rule protocol. The computer requires multiple independent sensor systems to confirm a threat before it allows an emergency stop. This protocol forces the system to ignore the radar's illusion. Navigating the complex illusions of the physical world requires a system that is deliberately programmed to doubt its own individual senses. Now imagine the environment degrades. Dense fog rolls in, or heavy rain blinds the optical lenses. A Level 3 autonomous system realizes it can no longer safely operate and must hand control back to the human driver. The immediate problem is the human. In a Level 3 vehicle, the driver is legally permitted to read a book or check their phone. They are completely tuned out of the driving task. Research shows that standard auditory beeps are ineffective at breaking that level of deep focus. To forcefully snap the driver's attention back to reality, engineers use multimodal physical warnings. The most effective is the brake pulse, a sudden, sharp physical jolt of the vehicle. By momentarily tapping the brakes, the car uses physical momentum to wake the driver up. This timeline shows the strict mathematical constraints of this process, known as the time of return, or TOR window. If the car forces the driver to take control too quickly, in less than 2.6 seconds, the human wakes up confused, leading to panic steering and dangerous swerves. But if the handoff takes longer than 6 seconds, the vehicle will have traveled too far down the highway to physically avoid a collision. The safe handoff window sits precisely in the middle of these two extremes. At this stage of autonomy, safety relies on the machine perfectly calculating the psychological threshold needed to safely wake up its human partner. Moving into dense urban environments, the challenges multiply. Look at the heavy, multi-layered roof sensor array on this Level 4 Waymo vehicle. It is designed to navigate chaotic intersections, like when a massive parked truck completely blocks the vehicle's view of a crosswalk. No onboard sensor can see through solid objects. This creates a dangerous blind spot where a pedestrian could step out with zero reaction time. This diagram illustrates virtual vision. The vehicle mathematically assumes a high-risk danger exists in any space it cannot actively observe, casting a bright red danger area behind the truck. To clear that shadow, the vehicle pieces together network data to reveal the hidden pedestrian. Utilizing this invisible data, the car proactively slows down before the pedestrian ever steps into view. The system shifts from purely reactive collision avoidance into intelligent defensive driving. Level 4 autonomy is defined by this ability to react to what the machine logically knows must exist in its blind spots. The governing philosophy tying all of this together is known as positive risk balance. The goal of autonomous driving is to create a system that reduces the overall total of accidents when compared directly to the track record of human drivers. While a self-driving car may encounter specific software errors a human never would, the measure of success is the statistical reduction of fatal mistakes. The machine has evolved, overcoming basic sensory illusions, managing complex human handoffs, and predicting unseen dangers in an urban grid. Through this evolution, the autonomous vehicle transitions from a simple mechanical tool into a contextual guardian, one that accounts for the invisible variables of the open road.